Hi, and welcome to this introductory video where we're looking at Poisson regression with SPSS. Now before we get into the regression part of it, let's just explore what a Poisson distribution actually is. The Poisson distribution is named after the French mathematician Simeon Denis Poisson. Poisson distributions are widely used discrete probability distributions, and that means they consist of numbers which are non-negative integer values, i.e. whole numbers, such as those that are associated with data based on counts of things. And typically they describe how often events such as visits to the zoo, insurance claims, or workplace accidents occur within a given time frame. And that means that the properties of the distribution are really useful for those who are working in applications that are focused on modeling often rarely occurring but quite important and sometimes unwanted events such as accidents or undesirable incidents. Some of the key properties of a Poisson distribution include concepts such as independence of events. And that simply means that each event or occurrence is independent of one another, and that one occurrence does not affect the probability that a subsequent event will occur, as one might find, for example, in things like time series data. Indeed, the number of goals scored in football matches have been found to follow a Poisson distribution, where if one team scores, it does not affect the likelihood that they will score again or that the opposition will score in response. A second property refers to what's called the constant mean rate, which simply says that in a Poisson distribution, the mean rate of occurrence of an event is constant over time. And in formula related to Poisson regression, this parameter is represented by the character lambda. Thirdly, Poisson distributions consist of discrete values, i.e. whole numbers, with no negative values, and that furthermore no two events can occur at the same time. Lastly, a curious aspect of the Poisson distribution is that lambda, i.e. the mean rate of occurrence, is equal to the variance. This means that the ratio of one to the other is equal to 1. That property is known as equidispersion. Now it's fair to say that analysts rarely find that the mean and variance are exactly equal. More commonly, we see situations where the variance is slightly larger than the mean, and we encounter what is known as overdispersion. In cases with severe overdispersion, there are alternative approaches that are available. More rarely, you may see situations where the mean is larger than the variance, in which case the ratio indicates underdispersion. Examples of where the Poisson distribution might be useful include situations where, for example, a cardiac unit wants to work out the probability that it will admit 6 patients within a 24-hour period, when on average they only admit 4. Or the probability that the mean number of unscheduled maintenance events for an aircraft within a year will increase by 50%. The Poisson distribution forms the basis of Poisson regression, which can be used to model count-based data such as predicting the number of traffic accidents at an intersection based on independent factors like weather conditions or the day of the week, or estimating the number of insurance claims that a business may make over a 5-year period. Understandably, people might well ask why not use ordinary least squares linear regression to predict counts of occurrences, and there may be certain circumstances or data sets or applications where in fact you can get away with doing that because the frequency of occurrence goes into right large numbers. We have 20 or 30 or 40 occurrences, or maybe up to 80 or hundreds of occurrences, and it may well be that linear regression works well in that particular set of circumstances. What tends to happen, however, when you're talking about counts of occurrences of events is that you're normally dealing with quite small numbers, quite small frequency values, and that secondly, OLS regression assumes something called homoscedasticity. This is where error values, i.e. the residuals, the difference between the prediction and the actual value, do not increase as the values of the predictors themselves increase, whereas count-based data does tend to exhibit this property. It's known as heteroscedasticity, and you can see it when you plot the residuals in a scatter plot. If it's homoscedastic, you'll get the same sort of variance as the values increase, and if it's heteroscedastic, you find that you get this funnel shape. And that is a violation of ordinary least squares regression. And it's, as I say, it's something which is commonly associated with count-based data. In fact, in data based on counts, you do tend to see skewed distributions with many low count observations and no values, of course, less than 0, because you're talking about counts of occurrences. And as a result, the residuals tend to be skewed as well. In fact, if you use something like OLS linear regression, you may well find that the predictions produce negative values, which of course doesn't make any sense when you're talking about counts of occurrences. Another aspect of count data is that they tend to exhibit non-linear relationships between the dependent and independent variables, especially when you're modeling low frequency occurrences. So you get these curvy linear relationships rather than these straight line relationships, which are of course more appropriate for linear regression. And something to bear in mind is that rather like logistic regression, Poisson regression transforms the data so that the initial raw outcome is being predicted actually as the natural log of the counted value. And that is then converted via a link function, just as logistic regression uses the link function, into the predicted counts, whereas logistic regression's link function creates a probability value, the probability of being in one of the outcome categories, the key outcome category. With Poisson regression, the link function transforms the result into predicted frequency counts. Now, earlier we did briefly touch on alternative approaches to Poisson regression. The obvious one is known as negative binomial regression, and negative binomial regression is most often employed when we're seeing over dispersion in the dependent variable, i.e. the variance exceeds the mean value and the ratio of one to the other is greater than 1. Negative binomial regression is slightly more complex than Poisson regression because it includes an additional dispersion parameter which attempts to adjust for this over dispersion. But nevertheless, in situations where the dependent variable exhibits over dispersion, using negative binomial regression doesn't guarantee that the model will be a better fit, and one should take care to compare one model against the other, Poisson versus negative binomial if you're concerned about it, and just make sure that it's worthwhile choosing one approach versus the other. One of the most notorious examples of data that follow a Poisson distribution relates to a famous data set from the 19th century concerned with deaths from horse kicks in the Prussian army. And the person who's credited with bringing it to light was the economist and statistician Ladislaw Bortkiewicz, who studied the death rates of Prussian officers killed by horse kicks between 1875 and 1894. And he used this as an example to demonstrate that events with a low frequency of occurrence in a large population can follow a Poisson distribution even when the probabilities of the events vary from one group to the next. In fact, he published his analysis in a seminal book entitled The Law of Small Numbers. And we can actually view that data in SPSS statistics itself. Let's have a look at it. And here we have the data within the SPSS statistics. You can see our key dependent variable here, deaths. We'll take a look at that in a moment. Which is simply occurrence, number of occurrences of death. It's an integer value with a minimum value of 0. We have the year that was recorded, and we actually have a number of different regiments or officer corps. Right click on that, you can see that there's a number of them here, one labeled simply G, the first corps, second corps, third corps, fourth corps. Each of them has a frequency of 20. And as I say, the number of years that the data was collected over ranges from 1875 to 1894. And finally, we have our dependent variable here. Let's just investigate that by going to Analyze down to Descriptive Statistics Frequencies. And we'll pick up our key field here, deaths from horse kicks. We'll go to Statistics and we'll ask, very importantly, for the mean, minimum, maximum, and the variance. Might as well ask for the standard deviation as well. And we'll ask for a chart. We'll actually ask for a bar chart here because although it's a continuous variable, the range of values isn't very large, so we should be able to see it quite clearly. We'll click OK at that point and look at the results. And here you can see that there were 51% of the number of events that occurred were actually 0 deaths, 32% of the records relate to one death. There actually are 0.7% two occurrences, two records where four death occurrences occurred, and that is a classic Poisson regression distribution. That's what it looks like. Very important, of course, when we look at the summary statistics, we can see the mean here is 0.7, and we can see the variance is 0.763, so it's very, very close to the mean. So there is that crucial property of the mean rate of occurrence, lambda being almost identical, almost the same as the variance value here. And buried away within SPSS, there is actually a statistical test that tries to test whether or not a particular distribution, a particular variable, follows a Poisson distribution. Now, generally speaking, I'm not a big fan of these kinds of tests, ones that test for normality, where you accept or reject a null hypothesis. And the same would be true here in this case, a Poisson distribution, whether or not we accept the null hypothesis, the data does in fact follow a Poisson distribution. I'm generally not a fan of them because they tend to be, rather oversensitive when you're particularly when you're dealing with very large data sets, and simply because you may end up rejecting the null hypothesis, including that the data doesn't exactly follow that particular distribution. It doesn't mean that you can't use it in a particular way. But in this case, I'm going to make an exception simply because the data set is a perfect example of indeed a Poisson distribution. To find this test, it's buried away. If you go to analyze here, you're going to go down to non-parametric tests, and you're actually going to go into the legacy dialogues and look for a one sample case. That's a Kolmogorov-Smirnov test. You can see here's a Poisson test here. Normal distribution, we don't need to test for that, so we can switch that off. Deaths from horse kicks is our test variable, and it asks us to put in the mean. I think the mean was about 0.7, so I'm going to put that in. Let's click OK at that point. And you can see here the asymptotic two-tailed distribution value here, the probability value, is actually equal to 1, meaning that we definitely would not reject the null hypothesis that the data follows a Poisson distribution. Now, having introduced the Poisson distribution, as well as exploring some of the key concepts associated with the Poisson distribution, and laid the groundwork for introducing Poisson regression, and finishing up here looking at a historical example of data that perfectly follows the Poisson distribution, we're now ready to move on to the next section, where we can perform Poisson regression within SPSS statistics itself.